Yeah. So we can treat the dimensions like an algebraic equation and cancel out and rearrange and simplify, just like we could with any other equation. What that allows us to do is find the units of constants and check equations to make sure they're valid. Checking for validity. First of all, any equation must have the same units on both the left-hand side and the right-hand side of the equal sign. You can't say that grams are equal to volts or meters squared are equal to meters cubed. You have to have the same dimensions on both sides. So a length can only be equal to a length, a mass can only be equal to a mass, and so on. Also, any terms added or subtracted from each other, so if you've got an equation where there are multiple terms, A plus B plus C, for a simple example, the dimensions of all those three must be the same, otherwise you can't add them together. We can't add nuts to bolts. Yeah. So, if the equation is valid in this way, it's said to be dimensionally homogeneous. Correct. To want a nicer, shorter, easier engineer's word. Dimensionally homogeneous, valid. Alright? Balanced. Everybody happy with that? So, let's look at an example. We're going to consider the equation for the period t in seconds of a pendulum of length L. It's given by, so that's the formula, t time of pendulum swing is equal to 2 pi times the square root of L, which is the length of the pendulum, over g, which is the acceleration due to gravity. Yeah? May or may not have come across that before. T is a period of time, so it has the dimensions t for time. And so what we need to do, if we're going to check that that formula, that equation is correct, that's dimensionally homogeneous, we need to check that the units of this side, the dimension, sorry, of that side, equal also t. Yeah? And this is where we're going to need that laws of indices we've done the first week, so that we can shift things around, cancel things out, and check. So, first of all, the 2 pi in front is just constant. It's the number 2 multiplied by the number pi, which is 3.14 and however many decimal places. It's unitless. So we can, in terms of dimensional analysis, we can forget that constant. Yeah? We can ignore 2 pi. What we have to do is say that the dimensions of the left-hand side, t, is equal to the dimensions of the right-hand side. So we've got a length, we've got a square root symbol, and then we've got a fraction inside where the dimensions of the top is L for length, and the dimensions of the bottom is G, which is acceleration due to gravity. And if you look back at your table from earlier, you'll see that the dimensions of acceleration are length times t to the minus 2. That's meters, standard SI units, and meters per second squared. Length times time to the minus 2. Everyone okay? Then what we do is we say the two lengths here cancel out, so it becomes 1 on the top, t to the minus 2 on the bottom. Yeah. We can bring that t up to the top by the laws of indices, and it becomes a positive 2. Do you remember that or not? Laws of indices, week 1. Negative index on the denominator can come up to the top and become a positive index. So we've then got the square root of t squared. The square and the square root cancel out, leaving dimensions of t. So we've proven that the dimensions of the left-hand side, t, are equal to the dimensions of the right-hand side by dimensional analysis and cancelling. What the red, all I've done is just highlighted that I'm cancelling L out actually. Yeah? Yeah. Okay? Alright? Yeah. Next bit. So, something else up front I said we could do is derive the dimensions of constants. So, an example, and you'll probably learn a bit more of this in your second year with Mr. Mark Winter when you do pneumatics and hydraulics. Bernoulli's equation. Have you heard of that before, Pete? No? I don't know the detail, but what it's saying is these are 3 pressures. Yeah? And when they're all added together, they equal a constant. It's one of these things where if one changes, the others will all change to match it, so the result is still a constant. Alright? What you've got is, you've got a pressure, one term, plus half times rho v squared. Rho is density, volume squared. Yeah. So there's some units there, and rho gz, rho is another density, g is the acceleration due to gravity, and z is a length. Alright, so p is pressure, rho is density, v is velocity, z is height, and g is acceleration due to gravity. And the question says, the example says, find the dimensions of this constant. What dimensions does it have? So we can use the dimensions of all the other quantities, yeah, and simplify them to find the dimensions of the constant. So, first of all, that constant there, oh yeah, Solly, what were you going to say? Pascals is that's the units of pressure, yeah, the SI units, right? The dimensions of pressure are whatever they were on that, they're ml minus 1t minus 2. Mass per length per time squared. Yeah. So half is just a constant. We can forget that in terms of dimensional analysis. It has dimension 1. Yeah. So pressure, if you look back at your chart, that's the P bit, has dimensions L, ml minus 1, T minus 2. This bit, mass times length to the minus 3, is density, mass per, so that's kilograms if you like, per length, meter cubed, kilograms per meter cubed, density, yeah? LT to the minus 1 is G, and then that's in brackets because we got a squarer. G is a velocity, it is squared in this side, so we have to square the dimensions, so they're in brackets. So LT to the minus 1 are the dimensions of G, and then we put brackets around there and square it because we want dimensions of V squared. Then we got rho again, to us at ml minus 3. G is lt to the minus 2. And z is a height to us length. So this is rho G Z. So that's where those dimensions come from, and the dimensions of the constant are equal to that. And that's what the question's asking us to find. Yeah? Remember that to add these three bracketed terms, they must all have the same dimensions. So we're going to use V and a squared. Yep. Part of my deliberate mistake. Alright, I'm going to move on to the next page. I've got the whole simplification type date, so that's clear. Okay. Sorry? Yes, yeah, all these go on. The original handout's empty, so this file empty, and work solutions to any problems, and videos go on Moodle here. Eventually, when I get around to do it. Everything's up to date on there at the moment. Okay. So that's our equation again. So I just repeated it at the top of the page because I didn't have room on the other page. The first thing I'm going to do is deal with these brackets here. Multiply out that LT to the minus 1 all squared. Now, the laws of indices says, you should remember, if we've got a to the x all raised to the power of y, the result is a to the x times y. Yeah? So we've got a power raised to another power, we multiply the powers. So looking here at this, we've got L to the minus 1 and T to the L to the 1, sorry, T to the minus 1. So that becomes L to the 2 times 1, 2 times 1, times T to the minus 2, minus 1 times 2. And L squared, T to the minus 2. So that's got rid of the brackets in this term. And there it is, put back in at L2, T minus 2. Yep. We're then going to take this middle term here and simplify it. This term here, we've got 1, 2 lots of L in there, so we can bring them together, can't we? We multiply items with the same base to different indices. What do? Laws of indices. A to the x times A to the y is equal to A to the x plus y. Yeah? So we've got L to the minus 3 times L to the 2 becomes L to the minus 3 times L to the 2, L to the minus 3 plus 2, L to the minus 1. We've simplified that middle term. If you look at that now, that middle term and the first term have now got the same units. We can add them together. Agreed? Yeah. So these two are the same. We said earlier, we've got to get all these three terms with the same units, otherwise we can't add them together. And then then lastly, we're going to simplify this one. You can see it. We've got a length, another length, and another length, all multiplied together. Yep. So we got minus 3, a 1, and a 1. Minus 3 plus 2 becomes L to the minus 1. Again, that's now the same as the others. All three have got the same units. ML minus 1, T minus 2. All three terms now. So we've got first one, ML minus 1, T minus 2. That was all that in the first place. Yep. Plus, when we simplify the middle term, we've got M, L minus 1, T minus 2. So that must be a pressure as well. So we can add them together because they're both pressures. And then lastly, the third term, we simplified that. That became M, L minus 1, T minus 2. So it's another pressure. We can add that together. Yep. So if they're all the same, the overall units, the constant, is a pressure plus a pressure plus another pressure equals the gas little thing that says pressure is constant. Mark will be a lot better than me at teaching you the mechanical theory around that equation. Okay, but it is dimensionally homogeneous and the constant has units of pressure. So each term has a unit of pressure. Have I lost anyone? Anyone who's really struggling? Be honest. A's heavy go, and I agree. Yeah. 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 You're gonna get, I tell you, you're gonna get something off the dimensional analysis in this place. Right? I'll be, anything you need for assignment, be given. Yeah, but yeah, lots of information about stuff like this online. But this is an engineering formula. This happens to be one that's not in my area of expertise. Yeah, that's in Mark's area of expertise and Adrian's. Yeah. So we just, I try and use a proper engineering equation rather than something like that. So we've had the pendulum swinging, and we've had Bernoulli's equation. Okay. Right. So, slightly different. Euler's number. Okay. This is another kind of constant thing as well. Euler's number It's just a number. It's a dimensionless parameter. Yeah? It has dimensions of 1. Given by the equation, Euler number is P for pressure divided by rho for density times velocity squared. Yeah? Using dimensional analysis, prove that the Euler number is dimensional, i.e. equal to 1. So what you've got to do, and I'm going to get you to have a go at it, write out this in form, so that your dimensions, the pressure on the top of the fraction, the pressure of density times velocity squared on the bottom of the fraction. Try and simplify them out. That the dimensions of this side is 1, proves that the dimensions of that side is also 1. I.e. everything cancels out and leaves the number 1. Alright, have a go, and we'll go through it afterwards.